Welcome to section 1.3 on cylinders. Let's take a look at the definition, 1.3.1. A cylinder is a surface that's made up of all the lines that are parallel to a given line and pass through a given plane curve. So it's a little bit easier to understand the definition through an example. So we'll do an example to see what that really looks like, but it's important to note right away, this does not match the definition of cylinder that you might know from high school. What you previously called a cylinder is more formally a closed right circular cylinder. Cylinders do not need to be closed. They can be open, they can be infinite, open-ended. Nor do they need to be circular. They can have any shape, as our examples are going to show us. So let's look at example 1.3.1. We're asked to draw the cylinder x squared plus y squared over 4 equals 1 in R3 and to name the shape of this graph. So if we go and take a quick look at that equation, the first thing we're going to see is that there is no z. So if there's no z, why are we being asked to graph this in R3? Shouldn't we be just graphing this in two variables, in R2? Well, let's have a quick look at what it looks like in R2, and then we can export this up to 3 dimensions. So if we're graphing this in R2, you might remember this curve from high school, and that is the curve or the graph of an ellipse. And that ellipse is going to have a longer axis in the y direction. So when x is 0, y is going to be either 2 or minus 2, and when y is 0, x is either minus 1 or 1. My bottom point looks like it's not quite far enough. Let's get rid of that and maybe put it down here. And so when we draw the ellipse, we're going to get a shape. It kind of cuts the axes like this. It's an okay looking ellipse. That's the idea, is that this is not a circle, it is an ellipse. And this ellipse is in R2, right? This is the x-axis and the y-axis. Well, if we want to embed this in R3, we've got an x-axis and a y-axis right here. So if we embed this in the plane where z is equal to 0 in the xy plane, we could draw our ellipse here, where this is minus 2 and 2, and this is 1 and minus 1. Now that's where z equals 0. So what about the other z values? For example, what if we wanted to draw the same ellipse up here when z equals 1? Well, there is no z value in that equation. So the shape of the equation is going to remain unchanged. In fact, I can just take this and copy it and paste it up here when z is equal to 1. And I'm going to get the exact same relationship between x and y because the z doesn't affect anything. It's not there. And in fact, that's true for any z I might choose. And is z down here? What if this is z is equal to minus 2 or any other z value for that matter? I'm going to get ellipses stacked upon each other, right, for any z value. And so those ellipses are going to fill up a surface. And that surface, right, that surface is going to be hollow down the middle, but it's going to be round, well, elliptical, actually, but open-ended. Right, there's that ellipse going around like this. Okay, so it is open on both sides. It is not closed. It is infinite, but elliptical. So this we would call an elliptical cylinder in R3. And the important thing to take away from this is that the z value, we have exactly the same shape for any z value because there's no z in the equation. So the z value does not affect the shape of the graph. And so that means that we end up with these graphs that are stacked along the z-axis, so that makes the graph parallel to the z-axis. And that's the first takeaway here. Takeaway 1. The graph of a cylinder is parallel to the coordinate axes whose variable is missing from the equation. So the previous example, it was z, and we were parallel to the z-axis because there was no z in the equation. Let's do one more example of drawing a cylinder. So example 1.3.2, now we're asked to draw the graph of z is equal to y squared in R3, and the name, the shape of this surface. So we notice right away that there's a variable missing. There is no x. And so we know our graph is going to be parallel to the x-axis. But let's go and graph that in 2 dimensions first. So in 2 dimensions, we can imagine graphing this in a zy plane, right, where this is the y-axis and this is the z-axis. And if we had the z is equal to y squared curve, well, that is everybody's favorite parabola. Z is equal to y. Sorry, z is equal to y squared. And if we embed that, well, it's quite convenient that the parabola lies perfectly, or the zy plane lies perfectly flat. We can just embed our parabola there. Now, in the same way, we have no x variable. So in the same way as the last example, we're going to get the same shape for any value of x. And so we know that means that our graph is going to be parallel to the x-axis, and it's going to have the same shape everywhere along, which is going to make it sort of an infinite parabolic tube. Now, if I were drawing this from scratch, I might not put this little bar here so that we have a little cleaner bit of a drawing. And I might add a few sort of lines here to give us the idea that that's curved, and I might shade this in, but the basic shape is what we're looking for. You get the idea. And so this, which kind of looks like an infinite feeding trough, right, for animals, this does not end, this keeps on going in both directions. I would call this a parabolic cylinder. So example 1.3.3, which of the solutions to the 2 previous examples, if either one, represents the graph of a function? Explain. So let's remind ourselves the functions need to pass, or the graphs of the functions need to pass the vertical line test. So the VLT, the vertical line test. So since we've got this one on the page already, let's go and take a look at example 1.3.2. Any vertical line that I draw is going to cut that graph at most once. So indeed, the surface in 1.3.2 is a function. But if we go and look at the previous example, our elliptical cylinder, a vertical line which just so happens to lie on the edge of those ellipses, that is going to cut our surface infinitely many times. And if that is the case, then example 1.3.1 is not a function because it fails the vertical line test. So the takeaway from this is that cylinders may be or may not be functions. In the next section, we're going to take a look at yet another kind of surface, the quadric surface, which again you're going to see may or may not be functions.